All right, kiddos. Welcome back to chapter 12, talking about non-linear regression. I hope you succeeded well with your homework and that it didn't actually take you 30 minutes a problem. Answers are in the book, of course, for the odd problems. You can check those later. And then 42, message me on Edmodo, and I can send you some help if you need it. All right, so today we're going to talk about the power model. Since you learned exponential last time, power model. Since you learned exponential last time, today's lesson on power is going to go much faster because you already understand the concept behind nonlinear, and power is only slightly different, only one little change. Okay, so here is the idea. A power model is the form y equals ax to the p. In other words, anything that has x raised to a power. So we came up with examples last time. Sorry, there we go. Y equals like x squared, y equals x to the 1/2. It doesn't matter what the number is, just the fact that the exponent is a number, that's what a power function is. All right, so it says that we're going to apply the log to both x and y. So let's see why that's true. This is definitely when you want to start writing things down in your notes. Okay, just like last time, let's start with our formula. Okay, so there's the basic equation for a power function. And we are going to do the same thing we did last time. We're going to log both sides. And let's see how that works out. Okay, let me throw a dotted line up there. The left side of the equation doesn't need to change. You have log of y, nothing needs to change. So I'm going to write log y, and it stays. Now on the right side, we have, sorry, it's a little sloppy, so let me rewrite it. Log of a times x to the p. So think back to our properties, think back to our properties that we wrote last time. How could this be simplified? Feel free to pause the video right now if you need a moment to think about it. Oh, that's right. I hear in the back of the room. Good job. You separate first the multiplication right here. So we have log a plus log x to the p. So just like last time, when there's multiplication inside, you can separate the two logs with addition. So we still have log y over here. Okay, whoop, don't give that away. Log y equals. Now, what else can be done? Not much. Log a is log a plus, that's right, the exponent can go out front. So we've got p times log x. All right, I'm going to take a moment for that to sink in. Very nice. It's linear. This right here, just like last time, is now a linear model. But what's the key difference here? How is this different from exponential? If you recall from exponential, we logged the y's. We did not log the x's. But look at what this proof is showing you. For power models, you do log the x's. See that difference? That's a big difference. Okay, so what that means, you have to take the log of x and y to transform a power function into a linear model. Okay, so let's give that a look. And starting with y equals 4x to the 5th. Okay, just like last class, I want you guys to try working that out. Okay, so try working that from the power model it is right now. Log both sides, see what happens. I will go ahead and pause the video right now, and when everyone's ready, hit play. Ah, you're back. All right, here we go. Everyone's all set to check your work. If I log both sides of this equation, log, we have log y equals log 4 plus, whoa, almost said the wrong thing, log 4 plus log x to the 5th. Then showing your work, next step, log y equals log 4 plus, move that 5 out front, so 5 log x. And if this was pre-calc, we would leave it just like that, but we don't want decimals. We don't want to leave all these logs as numbers. So like log 4, get that decimal. Log x, oh, you can't do anything with log x, it stays. Log y, it stays. So grab your calculator. Let me go grab mine. Sorry. Okay, log 4, you get point, which I'm sure you already got it. We get 0.6021 plus 5 times log x, and we have log y on the other side. All right, there's our transformed model. Notice it's still linear, right? We have no more exponents to worry about. We have y equals a plus b x. So we still have a linear model to work with. Whoops, go back here. This was the work shown for either exponential or logging or natural logs. So if you did either log or natural log, there's your work right there. Any questions? No? Oh, good job. You guys are so smart. Okay. Work this one backwards, just like last time. If I give you the equation, you guys need to be able to work it backwards. Step by step. So remember, if it's natural log, raise everything to its matching base, so e to both sides. Now, working it backwards is really similar. The e and the natural log cancel out, just like last time. So those gone, okay? But this time, it'll simplify slightly different. What can we do right here? Oh, that's right. Good job up front. I heard you say it. You separate them with multiplication, so you have e to the negative 5 times e to the 9 times natural log. Next step, this is where it's slightly different from exponential. E to the negative 5, you can get that decimal. What am I going to do is e to the 9 times natural log of x. Let me write that bigger. So up here, we have e, just this part, e to the 9 times natural log of x. Well, we've seen this before. You can rewrite them. So natural log of x times 9. And oh, look, the e and the natural log cancel. So you have x, oops, that's an exponent. Oopsies. That part should be an exponent. There. So because the e and the natural log have matching bases, they cancel. And this is an exponent on the x. Let's see. There we go. Whoops. Oh, it only wants to do one little tiny exponent. All right. So there's your inverse transformation equation. Oh, sorry, I didn't explain why that 9 switched. That was not. So this right here can be rewritten on the back as natural log x to the 9. And then you have e. So the e and the natural log cancel, which is why you're left with x to the 9th as your power function part. Okay? Alrighty, work this one, convert this one backwards. This is, once again, showing that we've got a power function. How can you tell by looking at this that this is instantly a power function, if I hadn't told you? Discuss with your partners. Pause this while we're waiting. Okay, great. You guys said it so quickly. Log of y and log of x. Remember the difference between exponential, x and y goes to x log y. That's exponential. Okay? If x and y go to log x log y, that's power. So we already know before we start that this is going to be a power function, but let's work it out. Raise both sides to 10 because that's the matching base for log. Those cancel. Go ahead and work this out. Pause the video. Oh, good, you're back already. 10 to the 0.5, check your work, times 10 to the 2 log x. Why is it why is it multiplication? Because remember, when these are exponents right here, and when you are when you are rewriting this addition, they separate through multiplication. All right, so 10y equals 10 to the 0.5. Feel free to use your calculators if you'd like. 3.16, 3.23 times, we still have this 10 to log x. Remember, the 2 can be rewritten as an exponent there. So I'll have 10 raised to the log x with 2 as the exponent up there. Exponent on x. 10 and log cancel. So we have y equals 3.1623 x squared. Because that's all that's left up here. That's all that's left from right there once the 10 and the log cancel. And here's your power model. How are you sure it's power? Because the exponent at the end is a number, not a variable. Good job. All right, here's how we're going to run our calculators today, friends. L1 is x, L2 is y, L3 will be your log of x's, L4 will be your log of y's. That's right, we have to log both x and y today because we're doing a power function. That's one of the main things you need to study to get ready for this test, is that an exponential only logs the y's, but a power logs x and y. From here, everything else is roughly the same. So here's our data. Go ahead, type it into your calculator. I'll give you a moment to do so. Pause this while you need to type it in. Okay, good. So we've got our planets in the solar system and the period in Earth years. Period meaning length of time to, what's the word? Rotate. Make one lap. All right, just like last time, start by making a scatter plot of the data. Very good. I'm sure yours looks exactly like this, and you are probably suspicious. Hey, that looks maybe a little curved, but you might be thinking it's exponential. That's why we have to go through the complete analysis. It doesn't look that far off from linear, so we need to make what first? Very good. A residual plot. So, just like always, from chapter 3, you have your x's in L1, your y's in L2, and now in L3, let's make our residuals. Go ahead and paste your equation, your least squares regression equation into y1, calculate your residuals, doing the usual, L2 minus y1 L1, and get your list of residuals. Don't forget to sketch your plot of x's with residuals. And yes, you quickly came across the fact, whoops, where's my residual plot? Sorry, I'm out of order. So my residual plot clearly shows, oh, that's not it either. I guess I deleted my slide with my residual plot, darn it. So yes, you can see from the residual plot on your calculator that it's definitely a curve, therefore not linear. All right, so now if it's not linear, you have to ask yourself, is it exponential or power? Which one? Who remembers from last class? What's the easiest and quickest way to decide now whether to do an exponential regression or a power regression? Very good. I appreciate you guys answering so well. That's right. You need to check your y ratios, which I'm sure you already did. You can compare them to this right here. Hi. That's our custodian coming in. Okay, so notice the what am I saying? Okay, sorry, distracted. This y ratio, not the same as this y ratio, not the same as this y ratio. Hopefully you're noticing these y ratios are not the same. That is because this is not exponential. So check your y ratios first. You know it's not exponential now. We can continue on with our power exploration. Okay, so power means we need to log the x's and the y's. All right. Now I know I said put log of x in 4 or 3 and log of y in 4, but you already used up L3 for your residuals. So you can put log of x's in L4, log of y's in L5. All right. Thank you very much. Okay, so continue on with this. So go to the top of L4, hit log x, I'm sorry, log of L1, because that's where you put your x's. Then go to the top of L5, type log of, that's right, L2, that's where you put your y's, hit enter. Now you have two lists with logged data. Let's check, make sure it's actually right. So when you, I should have had my calculator open already. Sorry, it's going to take a minute to open now. When we go to graph this, while we're waiting for the calculator to open, what two lists, or what two axes are we graphing this time? Very good. Pay close attention. Log x. This is the first time we're graphing something where the x-axis is not x. It's the log of x's, and the y-axis is the log of y's. So when you graph this, sorry, not the right data, second y equals, hit enter. What two lists do we want to look at our data to see if it's linear? Good. Log of x is in L4, and log of y is in L5. Graph these two. Oops. L4 with L5. And now zoom 9, you'll see our data. Sorry, I did not type the data in before I started this video. So we'll just steal this screen right over here. And when you hit zoom 9, you're going to see the beautiful graph. And of course, as you suspected, it's going to be gorgeously linear. Because we already knew from math, doing the math, logging x and y gives us linear data from a power function. Okay. Now what? That's right. Now that you know we have, we're on the right track, we need all of the least squares regression information now. Look up your y hat, look up your r, look up your r squared, and that's right, we need the new residual plot. Alrighty, so here we go. Yep. See, this is if you had gone further and tried to do exponential, you would have noticed it's still pretty terrible. So here is a quick visual. This was our original data. Looks kind of curved. This is your log of x with your log of y. Bam, nice and straight. Okay, so now we continue on. Whoops, there, you quickly find it. Okay, I've already shown it too long. So there's the least squares regression equation. By the way, on your calculator, you went stat. How did we get that? On your calculator, stat, calc, number 8, so least squares regression, with the two lists of logged data. So L4, comma, L5, comma, and I'm going to store it on Y1, on Y2. Vars, right, 1, 2. Okay? When you hit enter, you get the correct, I have the wrong data. You'll get the correct least squares regression equation, which is this right here. Now, you probably wrote this as log y and log x. That's totally fine. But the point is, you got a fantastic r, you got a fantastic r squared. You still need to make your residual plot, which will be, oops, I guess I should. When you make your residual plot for this, your x-axis, of course, nope, not the log, not the x's anymore. Very good, I heard someone say log x. And this is now the residuals of log y. Okay, so when you on your calculator go to graph this, you will be looking at what list are you going to put your residuals of the logs on? That's right, L6. It's finally time to use the sixth list, and we're all in the same problem still. So to get those residuals, remember we used to do L2 minus Y1 L1. But now we're not going to use L2 because we don't want just the y's. We want the log of y's. So where was that? Very good. L5 minus, we don't want Y1. That's right. Our new equation is in Y2. And do we want L1? Nope. We want our logged x's. So now we use sorry, I forgot where we put them. L4, because that's where we put our logged x's. Okay? Type this into the top of L6 and you will get your residual logs. So when you go to graph this, you're going to use your log x, which was in L4, and your log L6, that's where your residuals are. Whew. And you'll notice we get a fantastic scatter. It's a great residual plot. Take the time to look at it. Okay, finally, we're at the end. You know you've got a great model. It fits the data fantastically when it's linear. So now we need to transform it back into a usable power model. So here we go. Raise everything to 10 because we used logs. X and log, 10 and log cancel. Y hat, ooh, typo, equals 10 to the 0.0029, I feel like rounding, plus 1.4963 log x. All of that is an exponent right now. All right, and keep going. Split these now. We have y hat equals 10. Oh, I can get that. I'll just write it. 10 to the 0.0029 times, remember, to split this addition, they go together with multiplication. So times 10 raised to the 1.4963 log x. Alrighty, almost done. 10 to the 0.0029 times. Now remember, almost finished. This number can be rewritten as an exponent on the x. So let's do it. 10 raised to the log x to the exponent of 1.4963. 10 and log cancel, that was the whole point. Ta-da! We're finally done. 10, this part right here, 10 to the 0.0029, that comes out to be 10 to the 0.0029. You can do it on your calculator too, you don't need to wait for me. 1.0067 times x to the 1.4963. we're done. The 10 and the log cancel, so all that's left is this part right here. How do you know you've got a power function at the end? Once again, you have x raised to a number. Doesn't have to be a whole number, any number. It's now a power function. And like I showed you last time, let's check. Is that the perfect equation? Stat, calc, scroll down until you find the right one. Scrolling, scrolling. Nope, not there yet. There it is. Power regression. So on my calculator, it's A. Choose power regression. When you do power regression and use your original data, so L1 and L2, you're going to get this equation right here. And that's how you know for sure we have solved this correctly, everything's fine and perfect. Whew, that was a lot of fun work, 26 minutes for that one problem. So I hope you guys practice this. I'm scrolling through to see if I forgot anything. Nope, 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 looks fine, looks fine. Yep, 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 Wait, did we get the same? 0029, 14, yeah, 1.49, so often rounding, but anyway, oh no, it's fine. So that's the completion of a power regression. So we have the perfect model, and now of course you could be asked to make a prediction using this model, and you just plug in for X like always. Okay, you can message me questions on Edmodo. I will see you guys on Tuesday. We're still on target. Nothing's going to change our plan. On Tuesday, we will review because we have learned everything now. And on Thursday, November 19th, we are still going to have our chapter test covering all of Chapter 3 plus Section 12.2 on exponential and power regression. Hope this video helped. Have a great weekend, kids.